So, welcome again. We are reading this article titled Net 300 Gbps per lambda transmission over 2 kilometer of single mode fiber with a silicon photonics Mach Zehnder modulator. So, in that, let us me read again. Let me read this abstract again to understand or to recap that it is like that. Applying our 40 gigahertz bandwidth silicon photonics traveling wave Mach-Zehnder modulator, we demonstrate the transmission of 134 gigabaud PAM4 net 250 Gbps at a bit error rate below the 6.7% overhead hard decision forward error correction threshold of 3.8 into 10 to power minus 3 over 2 kilometer of standard single mode fiber in the O band with only linear feed forward equalizer. With the aid of nonlinear pre-distortion and FE, that is feed forward equalizer, we transmit 115 gigabaud PAM8 net 288 Gbps and net 305 Gbps PS PAM8 above the 19.02% overhead soft decision forward error correction with a normalized general mutual information, that is normalized general mutual information threshold of 0.8798. These results are the highest reported death rates for an all silicon modulator in an intensity modulation direct detection, that is IMDD system. So we have last time we read this introduction, we will not repeat this time again. Now moving to experimental setup, that is the section 2. Figure 2 represents the experimental setup along with offline DSP blocks to test the system performance. At the transmitter, let me see, this is the figure 2 experimental setup and offline DSP. AWG, that is arbitrary waveform generator, PDFA, that is preserved DM doped fiber amplifier, which must be used for O band signal amplification, PD photodetector, and RTO real time oscilloscope. So we can see here, this is the laser at 1300 2.8 nanometer that comes under O band. Then this is the silicon photonics projector modulator, which is this. So here this is optical signal and this is the electrical signal in RF reach radio frequency amplifier. And after that, this modulated signal has been passed through 2 kilometer single mode fiber. After that, presendomium doped fiber amplifier has been used instead of EDFA. This amplifier has been used to amplify the signal because EDFA is for C band conventional wavelength band amplification. And since as we are telling that in direct detection we do not use say balanced detector, we use direct photo detector here, the real time oscilloscope. So and here offline DSP block is given transmission at the transmission side. This is the DSP block. So pseudo random bit generator, then PAM symbol generation, then NL compensation, nonlinear compensation, resampling, RC pulse shaping, pre-emphasis, and then clipping and quantization. After that, it has gone to AWG, that is the arbitrary wave shape generator, then RF, and this is how the signal, that is the data generated at PRBS is being modulated. Okay, is modulated basically optical signal. And at the receiver side, we have another receiver DSP. Its job is to resampling, synchronization, low pass filter, then feed forward error correction, and Volantra post filter, maximum likelihood SD sequence detector, then bit error rate, and NGMI. This is the standard. So transmitter side and receiver side, we have DSPs. Okay, DSP, and this side TSP, and this is the transmission system. This is the modulator, this is the detector. This is the channel things. After 2 kilometer, presidium doped fiber amplifier has been used. Now, let us move to this. Figure 2 present the experimental setup along with offline DSP blocks to test the system performance. At the transmitter, an O-band tunable laser set at 1302.8 nanometer is used as the continuous wave light source, and 9 dBm of power is coupled into the modulator. So power is lambda is at 30.8 nanometer, and power is 9 dBm. 9 dBm optical power this laser is giving. This laser power is coupled to modulator using grating coupler. Okay, so this uh, the detail of modulator design and characterization are described in reference 10. The Magenta modulator with a 2.5 mm long phase shifter as a 3 dB bandwidth of 47 gigahertz and a DC of V pi DC V pi with potential used to have pi degree phase shift of 5.6 volt at 3 volt reverse bias voltage. The offline transmitter DSP includes PRSB sequence generator for different PAM format and lookup table based on linear pre-distortion. It is then followed by a resampling of generated symbol to the AWG sampling rate, that is the arbitrary wave shape generator sampling rate, and raised cosine pulse shaping, where the roll-up factor is empirically optimized at different symbol rate. To compensate for the low pass response of AWG, RF amplifier and RF cables signaled pre-emphasis of the transmitter RF chain is carried out before loading the signal into the memory of the 8-bit AWG tuning either at 128 Gbps uh, okay, yeah, Gbps or at 120 256 Gbps. The AWG output in both cases is amplified to about 3 voltage peak to peak voltage by an RF amplifier, that is the RF amplifier SHF807C with 55 gigahertz 3 dB bandwidth and applied to the silicon photonics magenta modulator using 67 gigahertz RF probe. After the modulator, the optical signal is transmitted over 2 kilometer of single mode fiber, a presidium doped fiber amplifier with a noise figure of 6.5 dB and 13 dB gain is used to compensate for the coupling and modulator loss and to ensure adequate optical power onto the 70 gigahertz pin photodetector. PIN photodetector, that which does not include a trans-impedance amplifier. Better light coupling via edge coupler and the use of trans, trans-impedance amplifier can significantly improve the receiver sensitivity, and the presidium dot fiber amplifier can be removed altogether for 2 kilometer range. The signal output of photodetector is then digitized by an RTO operation at real-time oscilloscope operating at 256 Gbps, and the bandwidth is set to 65 gigahertz, 75 uh, gigahertz when the AWG runs at 128 Gbps or 256 Gbps to filter out of band noise. Finally, the signal is processed offline by the receiver DSP as shown in figure 2 and is discussed in the following section. So this is the experimental detail of experimental results with 128 Gbps AWG. We first test the system performance of our magenta monitor for PAM4 and PAM6 format, which are the most promising option for the next generation DCI market. Figure 3a plots the BER versus gross bit rate curves with linear and non-linear equalization after 2 km of single mode fiber at 7.5 dBm receiver received optical power. At 250 Gbps PAM4. The signal equivalent of net 234 Gbps below the 6.7 HD FEC bit error rate threshold. Though the PAM6 format requires 25% less bandwidth at the same bit rate at this HDFEC BR threshold. PAM6 shows worse BR with only linear equalization due to its high SNR requirement and non-linearity is present in the system. With Volterra non-linear equalization, VNLE PAM6 outperformed PAM4 at this BR threshold. We use third order Volterra filter with a memory length of 96, 3 and 5 for linear second and third order Volterra kernel respectively, and 91 filter tabs for linear FFE for those results. It should be noted that for both PAM4 and PAM6, the improvement with VNLE diminishes at symbol rates close to 128 gigabaud. The signal swing out of the AWG becomes smaller due to the stronger pre-emphasis and the system non-linearity in no longer dominate at high symbol rates. Therefore, considering the complexity of VNLE, the curves show that with a high bandwidth silicon photonics magnetic modulator, PAM4 is a suitable choice for PAM for 250 Gbps. So here the author tries to prove that PAM4 is a suitable choice compared to PAM6. So we have to make here table advantage and disadvantage of PAM4 and PAM6. Next, we transmit PAM8 signal at different symbol rates and due to its high error floor compared to PAM4, we choose SDFAC instead of HDFAC. We calculate the MGMI a suitable performance matrix for SDFAC and consider a 902, 19.02% overhead concatenated FAC code with an MGMI threshold of 0.8798. The NGMI comes in figure 3 and the histogram of received symbol at 100 gigabaud PAM8 in figure 3C reveals the presence of strong non-linearity in the system, which results in significant error from the outermost level. We use a peak-to-peak driving voltage of 3 volts, 55% of the DC V pi of the modulator, and a bias magnetic modulator at the quadrature point. This indicates that the non-linearity mostly comes from the RF amplifier, which shows a 1 dB output power compression at 50 dBm. Although lowering the input to the amplifier reduces the nonlinear effect, the lower modulation driving signal decreases the optical modulation amplitude and degrade overall system performance. To overcome this issue, we adopt a nonlinear compensation techniques by means of nonlinear lookup table with three symbols memory length and compare its performance with nonlinear LE, both nonlinear pre-distortion with FFE and third order VNLE. Without any pre-compensation shows similar performance and we can successfully transmit 336 Gbps PAM8 over 2 km of single mode fiber. Increasing the nonlinearity memory length of VNLE beyond the previously mentioned value do not improve the system performance significantly and is thus not adopted for these results. Unlike PAM4 and PAM6 due to higher number of inner levels and high peak to average power ratio of the transmitted signal, non-linear equalization or pre-distortion give better results of PAM8 for all symbol rates of interest. So with this, we will come back at reading section 4 next time. See you.